All right, good morning. Pre-calculus. I'm going to spend some time on hopefully answering some questions on this stuff, but I'm going to work some of the homework exercises also. I want to take a look at some stuff that I noticed I didn't write about in the original announcement from 7.2. We're doing trig function of inverse trig function of something, and that is kind of a useful idea. It's a little different approach, uses the right triangle a lot more, and being able to rewrite these expressions is leading into something that is a very important topic in calculus later on. So I do want to spend a little time on that, these right triangle exercises. Interesting use of it. So I'll work through some of those, but then any questions that you have on the other stuff, let me know. I'm going to do some exercises out of the textbook in 7.2 first. I'll get that set up. Hopefully you can follow these examples if you're still working on those all later on this week. Let me get this ready to view. Okay. Trig equations, I wrote some stuff about Monday's announcement. And I left some links for that, but I think this trig of inverse trig stuff is a different topic, and I want to spend some time on that now. So I didn't really do an intro to that. They're strange things to think about. These are inverses of each other, sort of. So you would think something useful would happen here, but I'm talking about situations where this is one trig function, and this is a different inverse trig function. They don't really match up. How does that going to work? So, for example, number 16. You got something in here. You have an inverse trig function of it, and then a trig function of that. But tangent of inverse tangent of square root of 3 would probably just be the square root of 3, right? I say probably because we have to think about quadrant stuff whenever the inverse tangent things are involved, inverse functions are involved. But secant of inverse tangent doesn't seem like anything nice would happen there, but it does. Kind of nice. We got to see what this ends up looking like. In cases where this is just a number like this one, the calculator knows how to do these things numerically, and we can get a numerical answer to it out of the calculator. I haven't worked through one of those in a calculator because it's really kind of easier to do on paper, but I don't want to think about what happens there. So see if I can think this through on here. I would want to make sure I'm in radian mode on all this for all of these. I think I am for this one. But the process that we're going through on this for secant of inverse tangent would be a little bit of a pain, but we start with the square root of 3. We're going to take the inverse tangent. I'm going to do what's inside here first. So inverse tangent of square root of 3 is this number. If I'm taking the inverse tangent of something, I'm ending up with an angle. That thing is an angle in radians. And then I'm going to take the secant of that angle. Trig function of that angle gives me back some kind of ratio. So this is in radians, but the answer is just going to be a number again. But secant, I don't have a button for. Secant's reciprocal of cosine. So I got to do 1 over cosine of that answer that I just had. So you can set that up. And that comes back up to 2. So somehow this whole thing is equal to 2. And I want to see why that is, sort of geometrically what's going on with these, because there's a little drawing that helps with these. And if this is a numerical thing, then we're just working through what's going to give us this number. But if this is an expression, I got to be able to rewrite this expression without using all these fancy functions. Essentially, we're taking a number, going over to radians, and then going back to a number right here. We don't have to use all this fancy stuff to do it. We can just set up what that expression is. Use a little triangle to do it. We're going to see how this comes out to. By thinking through what happens in a triangle on this one. This is a right triangle. I'm not even trying to draw it to scale, but this is some right triangle. When you say inverse tangent of square root of 3, that means the angle whose tangent is square root of 3 or square root of 3 over 1. The tangent of some angle is square root of 3 over 1. That's opposite over adjacent. That's tangent is opposite over adjacent, or y over x here. So they're telling you there's an angle somewhere where this ratio would happen. So there's this triangle, and this is my angle right here. And I want the secant of that angle, which is reciprocal of cosine, so it's hypotenuse over adjacent. Well, wait, I don't know the hypotenuse on this yet, so I got to stop and think that through. 1 squared plus square root of 3 squared equals the hypotenuse squared. So that's 4. So the hypotenuse is equal to 2. Square root of 4 is 2. That's the hypotenuse. You can always fill in the third side of the triangle, and then you're just doing the ratio here. Secant is hypotenuse over adjacent. So we just get 2 over 1 is 2. Sure enough, we can just get that out of the triangle. Once you're used to it, that's actually quicker in a lot of cases than pulling out the calculator for that. It's just a little triangle drawing. We might have a negative value involved. We might have a few different things going on, but we want to be able to work through these and get the right ratio at the end of it. So a couple examples on that to work through it. Then we've got one where it's an inverse trig function of a trig. No, I didn't get into those. Good, okay. Just this kind of thing. Here's number 31. Sine of, and this one's got brackets for some reason, but inverse tangent of negative 3 says find the exact value of each expression. So this one came out to a nice number. It was just 2. That was the exact value. Calculator answer to this one's not going to look so nice because it's not such a nice number. Decimal wouldn't really help me here, so I'm going to do this by the triangle thing. We can check it with the calculator, but there's a right triangle somewhere, and I'm not trying to draw it accurately. There's a right triangle somewhere. There's an angle in it whose tangent is negative 3 or negative 3 over 1, and that's the tangent to the angle, so that's opposite over adjacent. Wait, that's a negative opposite side, so my triangle doesn't really look like this. I guess it looks like this instead. I got negative 3 over 1. Inverse tangent's going to actually be over here. So I guess I'm talking about a fourth quadrant thing. But these are the y and the x for that one. Again, I can solve the third side using Pythagorean theorem. 1 squared plus negative 3 squared is 10. So the hypotenuse squared is 10. So the hypotenuse is radical 10. That would be the third side of the triangle. And then this is my angle. So the sine of this angle, sine is opposite over hypotenuse. Opposite over hypotenuse is negative 3 over square root of 10. That's the sine of that thing. Or If you're into rationalizing the denominator, you might write it this way, but that's the value that we're getting from sine of inverse tangent of negative 3. Should come out to this. That's the exact value of it. Calculator is not going to give me a very nice expression for that. If I try inverse tangent of negative 3, I get that crazy looking thing. That is a fourth quadrant angle. And I want the sine of that angle. See if I can get this readable. Inverse tangent of negative 3 is that thing. Sine of that thing is negative 0.9486832981. Well, that's approximate. That's not the exact value of it. It's kind of a lot of decimal places, but that's not exact. That is this value. I mean, if I do, just to compare it, negative 3 times square root of 10 divided by 10, I get, oh look, negative 0.9486832981. So that's working. They do come out to the same numerical value with them. So this is right. But pretty quick to do by drawing a triangle. If you, once you get the hang of the three sides of the triangle, the right triangle thing takes care of that for us. So we could actually have a nice way of rewriting things like this. And you do get some of these with letters in there instead of numbers in there. So this one's not a numerical question, but we can simplify this kind of situation whenever we have trig function of inverse trig function of something. So I could make up any of these things. I could do sine of cosecant inverse of x. And you're putting together trig function of inverse trig function of something. There's a nice way to write it using the triangles. And we don't need all these fancy functions in there. We can get this written just with algebraic stuff. So I'm going to think of that as x over 1. And I'm going to draw a triangle for it. Cosecant of an angle is the reciprocal of sine, so it's hypotenuse over opposite. I got to keep track of these things, but stop and think. Sine is opposite over hypotenuse, so cosecant is hypotenuse over opposite. So this looks like hypotenuse x opposite 1. This is my angle. And so the third side of the triangle, well, this is my adjacent side. And it turns out that the adjacent squared plus 1 squared has to equal x squared. So the adjacent side squared plus 1 equals x squared. So the adjacent squared is x squared minus 1. So my adjacent side would be the square root of x squared minus 1. Square root of x squared minus 1 is what's going to be here. And I don't know what that angle is, but the sine of that angle is just opposite over hypotenuse. Wait, that's just 1 over x. All right, so that one is kind of simple because cosecant's the reciprocal of sine, so that turned out nice. But I could do any of those things. I could do this. I could do, if I wanted cosine of cosecant inverse of x over 1. That's the same piece on the inside, so it's the same triangle. The cosine of that angle would be adjacent over hypotenuse. I can do any of these things off from that same triangle picture. So get used to drawing that out. And you can rewrite this expression that involved all these fancy functions into something that's just algebraic. That's kind of a nice thing to have. I wish I could say that you'll appreciate this next week or the week after, but it's actually pretty deep into calculus before you run into this situation. So I want you to see it. I want you to have some familiarity with those. That's one of our learning outcomes. Doesn't really connect to the other ideas of functions that we're dealing with until much later. But those are simple little problems once you get the hang of drawing it out. You get a lot of practice with these ideas about what is adjacent over hypotenuse and opposite over adjacent and all those things. Right, triangle stuff is actually the right way to think about that.
Things I gotta remember to do for deal with mom.
Now I want to work through some equations here also, so you have some examples of how this stuff works. My thought process for solving equations when there's trig stuff involved in them. Is still that I'm going to try to get rid of the most complicated thing first. And we're not going to be able to spend a ton of time on a ton of complicated stuff, but want to look at it and try to take care of the most complicated thing first. I'm going to tackle a pretty complicated looking one to start off with. Number 65.
Not today. Not today.
7.3. So these equations are going to show up toward the end of the homework here, but number 65 is similar to one of those. I got sine squared theta minus cosine squared theta equals 1 plus cosine theta. Solve each equation on the interval from 0 to 2 pi. So for this one, they're just asking for solutions on the interval from 0 to 2 pi. These are periodic functions. Period is 2 pi, so these solutions are all going to be repeated between 2 pi and 4 pi, and again between 4 pi and 6 pi, and again between 6 pi and 8 pi, and so forth. But I don't need all of them. I just need the ones in that first cycle there. So the unit circle goes from 0 to 2 pi, and I want to think about that. There's usually a couple of solutions there. We'll see what happens with this one. But my thought process is to try to get rid of complicated stuff. Looking at this, I've got squareds in there. I'm probably going to get rid of those by factoring. But the complicated thing with this one is that I got cosines and sines. I'd really rather just have one or the other. And the nice thing is I got identities for that, especially for the squareds. So since sine squared of whatever plus cosine squared of it is always equal to 1. That's the key identity to these. That means I can always rewrite one of these in terms of the other if I have the squared, especially. Sine squared theta is 1 minus cosine squared of theta. So it's easy to swap one of these for the other. And that's the first thing that I want to do on this. I'm getting darker for some reason, but I'm all right on it. Sine squared is 1 minus cosine squared. I can drop that in and put everything in terms of cosine. All cosine. Since sine squared is equal to 1 minus cosine squared theta, I'm going to make that, use that identity. Now I have everything written in terms of cosine. Combine the like terms, sine squared theta. Most complicated thing now is the exponent on that. And so I want to try to get rid of the exponent by factoring. I'm going to use zero factor property. I want to get everything to one side and see if I can factor this thing. So I'll give you two ways of thinking about this. From this point, where you've got it all down in terms of one trig function, here's two ways of thinking about this. The first is it's a handy idea to get used to. What if I just go to algebra land about it? So I'm going to just substitute in some other letter in place of cosine theta so I can think this through. Instead of dealing with fancy trig looking stuff, I just and think about just algebra. That's more comfortable for a lot of people. Right? 1 minus 2u squared equals 1 plus u. That looks like an algebra problem. And so, no. Your algebra instincts should tell you, oh, I just want to get everything to one side to use the factors. So I'm going to move everything over. Subtract 1 from both sides. Those are actually the same on both sides. So I just have 2u squared plus u equals 0. Factors. Zero factor property says either u is equal to 0 or 2u plus 1 is equal to 0. So u is 0 or u is negative 1/2. And it feels like I'm done, but I'm not, because I'm trying to solve for theta in this. So this is when I have to undo the substitution up here. U is cosine theta. So I'm really asking, what is theta when cosine is 0? Or what is theta when cosine of theta is negative 1/2? And I need my inverse trig functions there, or my unit circle for that. Cosine is equal to 0 here on the unit circle when x is 0. So at pi over 2 or 3 pi over 2. Cosine is equal to negative 1/2 here and here. That's actually 2 pi over 3 and 2 pi minus 2 pi over 3 is 4 pi over 3. So those are our solutions between 0 and 2 pi. The unit circle shows them all. You got this one and that one. If you're into inverse trig functions, the inverse cosine of 0 is going to come out to pi over 2. And you've got to realize that there's also this one in the opposite quadrants there. And the inverse cosine of negative 1/2 is going to give you this value. And you got to realize there's also one in the third quadrant here. So you got to think about the quadrants to get them all. But those are all your solutions between 0 and 2 pi. That's what we were looking for, those 4 values. Now, this isn't really much different, but the second way of thinking about this, if you don't involve some other letter, you can actually do all this in terms of cosine without dealing with the letter.
Oh, yeah, you do. But you don't need, yeah, you can use it like a small. I can do that. The other thing is,
I can just move everything to one side. It's still going to get the 0 on both sides, so you can subtract the 1 from both sides and move this over just like we did. 2 cosine squared theta plus cosine theta. I'm still going to use the 0 factor property. I'm just doing it without making that substitution, just keeping it in terms of cosine all along. You can factor out cosine theta. 2 cosine theta plus 1. There we go. And then the 0 factor property says either this is equal to 0 or 2 cosine theta plus 1 equals 0. So cosine theta is negative 1/2. Both of those things. So we're right back to here and ready to draw the unit circle part of it.
yeah.
Or do your inverse cosines and think about your quadrants. That's my big caution on these that you have to get used to. When you get to the end of a trig equation, if you're just getting theta by itself, you're going to do inverse cosine of 0 and you're going to get pi over 2. That's one of the answers. And when you do the inverse cosine here, you're going to get, comes out 2 pi over 3. That's one of the answers. You got to recognize those other ones are there. So you really got to think about the unit circle. If you want all the solutions between 0 and 2 pi, they usually come in 2 different quadrants, and we got to work that out on the picture. That's
Yeah.
unit circle trig stuff. So all the different interpretations of trig come in handy. The right triangle stuff is the right way to handle that trig of inverse trig situation, and the unit circle is really handy for equations. Solving the trig equations, that's pretty important also. There's a lot more variety of what can happen with equations. I don't want to get too deep into it because we're trying to do the basics on this, but I should work through one more example on this. I did this one twice, but I'm going to work through one other example on it.
But you can do it in English, and if you do it in English, you could say, you know,
Number 71.
yeah, it's a charger, we'll have a charger for you, and you just plug it in, and you never have to worry about it.
I'm gonna look at number 71 here.
Case, so you can set it upright. So you can see it.
7.3, number 71.
Yeah.
You know, when I was thinking about it, telephones, the big thing, but you know,
Tangent theta equals 2 sine theta. And I want to do some graphical stuff on this also to think this through, but because we're trying to remember what these graphs look like also, but you don't really need it for the equation. I'm just going to tie that up. Most complicated thing is that I have more than one trig function involved. I got tangents and sines, and you want to get it down to just one trig function somehow if we can. So I'm going to try to do that. Tangent or secant or any of those, they can be written in terms of sine and cosine easily. Write down what they are in terms of sine and cosine, and you get rid of the other stuff. Now I got both sine and cosine in there. But
it's amazing.
both sides are actually multiplied by sine theta. You might be thinking cross multiply right here, which would be a good way to start. Some of these sines are going to cancel. When you cross multiply, you get 1 sine theta equals 2 sine theta cosine theta. And either way, the sine is going to cancel from both sides. Both sides are multiplied by sine theta. So when we divide that out, you get something simpler here. You get 1 equals 2 cosine theta. Now, I can't just divide both sides by something without thinking about whether it's equal to 0 right here or not. One of the possibilities with this is that sine theta is equal to 0. And what would happen then? Well, that would actually be a solution to this equation. If sine was equal to 0, these are both going to equal 0. That would actually work as solutions. So that leads to some solutions. Sine is equal to 0 at these 2 points on the unit circle, when y is 0 here. So at 0, pi, 2 pi actually we throw in. Those are the values where sine is equal to 0. Those are solutions of the original thing. But then we're going to get more solutions from this piece. Divide by the 2. You got cosine theta equals 1/2. So on the unit circle, that's 1/2 is up here. This is like pi over 3. That's the inverse cosine of 1/2. And the other quadrant would be, I could say minus pi over 3, but really it's in the fourth quadrant. It's 2 pi minus pi over 3 is 5 pi over 3. These extra quadrant things, we got to get used to dealing with that. Let me put it up where you can see it. Well, if the values are here and here, you got the original value, and you got 2 pi minus that is your fourth quadrant one. Those are the two solutions between 0 and 2 pi for that one. Now this was asking for solutions on the interval from 0 to 2 pi. To be really precise, it actually says theta is greater than or equal to 0, but less than 2 pi. So I'm not actually going to include the 2 pi. My list would just be 0. Pi over 3, pi, and 5 pi over 3. Those are in order. I just set these two solutions and these two solutions in numerical order right there. But that's my whole set of solutions between 0 and 2 pi. And that's pretty, those are pretty typical of how these equations go and the skills needed for it. It is kind of pulling together your algebra instincts with the use of different trig identities. We do stuff with sine squared plus cosine squared equals 1 a lot. And we do stuff like, of course, tangent being sine over cosine. Those are trig identities. These kinds of trig identities, as well as the tools of algebra like cross multiplying and zero factor property and stuff like that. To be careful dividing both sides by that, I want to express the alternate right here for a minute. If I hadn't divided by that, I would be wanting to move everything to one side on this, and I could set this up subtracting sine from both sides.
That little pencil is $100.
With subtraction, 2 sine theta cosine theta minus sine theta equals 0.
Okay, when I look at it,
Then I could use the zero factor property. I didn't get down to just one variable, but they're going to separate out into 2 separate factors also. So when I use my zero factor property, I'm either looking for where sine is equal to 0 or where cosine theta 2 cosine theta minus 1 equals 0. So you get the same 2 situations that we looked at there. Could have done that by factoring instead of using the division thing. We do get all of those solutions. Now I want to compare that back to sketches because we're all pre-calculus people and we should think in terms of graphs of a function. So that's one of the things that should come to mind. I left some space at the top of this paper because I want to go back and think about how this looks. In terms of the sketches of these functions, it's not going to tell you where the answers are, but it's going to kind of tell you how many there are. The sketch of tangent bit, if I go to the graph of the function between 0 and 2 pi for theta, or really thinking tangent of x and 2 sine of x, because I'm not thinking of theta as an angle, I'm thinking of x values along the axis. Function graphs. The tangent function looks like this, has the asymptote at pi over 2, and this. That's your graph for the trig function. It continues going on like that. Wait. Next asymptote is actually at 3 pi over 2. So actually, if I want to go all the way out to 2 pi, I'd have another piece here. So that's the graph of a tangent function between 0 and 2 pi, 2 cycles of it. Compare that to this one. I want to know where that function is equal to 2, 0, and 2 pi. It's going to go up and down. It's multiplied by 2, but it goes up. Pi is where it's going to hit the ground. Here are the x-axis again. So your 2 sine x would go up and down in that interval. And we'd have some solutions where these functions are equal. One of them is right here before you get to pi over 2. Well, one of them is right here. One of them's here. They cross again at pi, and then they cross again somewhere after 3 pi over 2, somewhere in that the fourth quadrant. So that's my 0. One ended up, it's hard to tell on the graph, but it ended up being at pi over 3, pi, and this one ended up being 5 pi over 3. So that's the right number of solutions to get there. And thinking through those sketches at least helps you count the solutions, make sure you got the right number, make sure you got that full list there at the bottom. Whether that's true. Some of the solutions are pretty obvious on there. Some of them you still got to work out the algebra on. If that helps. We got to remember what these graphs look like. Anyway, we're trying to get more used to that.
Yeah.
All right. Now, when it asks for all solutions, you need like a pattern to show where all of the solutions are. Some of these it says give a general formula for all solutions. I want to think that through. Tackle one of these things. They do that for the simpler equations, but we need to know how to do that also. Because, right, if you have a graph like this, you got all those solutions. All of them are going to happen again out here on the graph and again and again. So we could have more solutions than that. I'm going to do a simpler one, but giving all solutions. This is actually number 42.
Yeah, I would not. No, I don't think so.
This is a formula for all solutions. We're not going to list them all because they go on forever. Right? It's periodic. We get a list or a formula for all solutions. The list would go on forever, but there's pattern to it, so we can write a formula for them. This is already like a simple equation. We've already got just one trig function, and it's already by itself in this. So they didn't leave you much algebra to do. We're already to here, but we want to think about where this is true. What are the trig where it comes out to square root of 2 over 2. Sine is positive, so we're in these two quadrants. Square root of 2 over 2 is actually the value at 45 degrees, or pi over 4. But it's also true. Same y value over here. That's 3 pi over 4. Gotta get good with these trig. Exact values, they use those a lot. If you do inverse sine of this, you should get pi over 4. Of course, the second quadrant one's also true. And that's it. 4, go from 0 to 2 pi, that's it. But we're going to get, if I go all the way around and up, and so on. So the solution, 4 pi over 4 plus 2 pi. 4 pi over 4 plus 4 pi, and so on. And I could actually go in the direction too with minus 2 pi. Or separately, the second quadrant ones are at 3 pi over 4, 3 pi over 4 plus 2 pi, and so on. Or 3 pi over 4 minus 2 pi, and so on. So a formula for that, a nice way of saying that without having to use ... stuff, you can express the solution. I'm going to try to write a little bit. You can express the solution as pi over 4 plus any multiple of 2 pi or 3 pi over 4 plus 2n pi, where n is any integer in here, right? The negative integers would be included, positive integers would be included. 2 times that, so we only get the even multiples of that. That's the list of all of them for all n. You might see this symbol, n in z, means n is any integer. Those two things are going to represent all of those two lists of equations. So all that I need is the solutions between 0 and 2 pi, and then this little multiple of the period right here. If the period of the function was different, I might have something other than 2 pi times my n. If you had a function with a different period right there, that's getting into fancier stuff, but that's the basic idea. Throw one more in with a different period right here, just to show what happens with that. That's number 43. And the book is cosine 2 theta equals -1/2. Here's where we use our graph. I've sketched the graph, but I have to think in terms of what is the period on this graph right here. Period was 2 pi over b, or 2 pi over this. Omega is 2. So that comes out to pi. This is actually period pi, so they're going to repeat every pi units. It's going to be any multiple of pi that's in there. And I need all of the solutions that happen between 0 and pi on this. Now, solving it out, I can still go to the unit circle. I got one trig function all by itself in this. So it's wherever cosine is equal to -1/2, which is, that's pi over 6, pi plus pi over 6, 7 pi over 6, and 2 pi minus pi over 6 is 11 pi over 6. Got to get good with these. I mean, if you're a calculator person, you have to be able to work around being a calculator person a little bit. But if you got to this point, you want to get rid of cosine. You're doing the inverse cosine of -1/2. Hopefully you recognize the value that you get out of that. When you do inverse cosine of -1/2, hopefully you recognize that as wrong, because that's pi over 2. I didn't put the parentheses in there like I should. So hopefully you recognize that's wrong. Hold on. Inverse cosine of -1/2 as an input comes out to that. Now that doesn't look like anything to me. That doesn't look like the right thing. I drew the picture wrong. Calculator's right and I'm wrong on this. That's a good thing about doing them in the calculator also, is you recognize what ain't right. That's a second quadrant thing, and it should be a second quadrant thing. So back up a little. I got to fix my picture. How did I get in the wrong quadrants? I drew the wrong thing. I drew where sines equal to -1/2. Those aren't right. I want cosine equal to -1/2 instead. This is x value on this. So it's here and there. This is
not mine.
2 pi over 3. Pi plus pi over 3 is 4 pi over 3. That's more like it. That's what this number was. Second quadrant. That's 2 pi over 3. If you didn't recognize it. Maybe you got one of them fancy calculators that'll show you the exact value on something like that. But if you have regular settings on the calculator, you got to compare it this way. But 2 pi over 3 is 2. That's the one that we got. Calculator doesn't know about these other quadrants because inverse cosine is only existing in these two quadrants. It only takes the part of the cosine function that was first and second quadrant. So you always got to recognize the other ones. Okay, those are the two solutions in this period. So my full list of solutions is 2 pi over 3 plus any multiple of pi, or 4 pi over 3 plus any multiple of pi would also work. Still wrong. Okay, I made another mistake on this. This is not my morning. So if you're watching through this, I hope you don't stop too soon because I got to fix a bunch of problems on it. I forgot about this 2 to deal with right here. What I just found on the unit circle was where 2 theta is equal to this, or 2 theta is equal to this. I got to do the dividing by 2. So theta is actually pi over 3, or theta equals 2 pi over 3. That's what I should have had for my solutions to begin with. So I got this part right, but I got this part wrong. Pi over 3 and 2 pi over 3 are the original ones. That's the correct answer. Now I fixed that. All right, I spent a lot of time getting that one wrong, but I hope I've illustrated the ideas there a little bit that'll be useful to you. Let me know about questions as you go along if you get stuck on anything. Some of these you got answers in the back of the book for. You can tell if something's going wrong. And certainly the exercises in side book, they give you some feedback there. So I hope all that stuff helps. Let me know as the week goes along what you're having trouble with. I'll try to be in touch. Have a good day.